So Easton walks from his house to the bank and then to the grocery store before returning home. The graph shows his distance from home, D of t, in miles t minutes after leaving his home. First question, how long does the trip take him in total? Got to like call on y'all? Is that what I need to do? Do I need to use? Okay. 75 minutes. How'd you come up with that? That's pretty good. That's pretty good. That's exactly correct. This represents his distance. His distance is back 0 from home, and that's at around 75 minutes. Questions on that one? B, how many minutes is Easton at the grocery store, and how do you know? How do you know? That is correct. You can see his first stop was the bank, so that's the first flat part, or the first horizontal part. The second one is here, and that goes between minutes 40 and 55. And so you could just subtract 55 minus 40 gives 15 minutes. And it says, how did you know? Kind of explain how you knew that was a stop.
Movement is constant.
Right, his distance from home stays the same. So he has to be stopped somewhere. Okay, good. Questions on B? Like I said, there's different ways you could explain it. Y'all were talking about the flat parts of the graph, right? How did we know that the flat parts meant he was stopped? Because his distance isn't moving. C, on which time interval is D increasing?
To 20 minutes and 30 to 40 minutes.
I agree. That's not what answer they have. I'm going to say they're wrong. Okay, so D is increasing right here. We're going from 0 to 1.5. That's from 0 to 20 minutes. So we could say when 0 is less than t, which is less than 20. That's one way we could say the interval. Another way you could do it is on interval notation. Have you guys seen interval notation before? 0, 20. It kind of looks like an ordered pair, but it's not. A lot of times, I need to write on here. A lot of times with the interval notation, sometimes we use braces or brackets. Sorry. Right? Have you guys seen that before? For increasing, decreasing, and constant, we never put the bracket. It's never included. Increasing, decreasing, constant is always in parentheses. So from 0 to 20 minutes, D is increasing, and D is also increasing from 30 to 40 minutes. And another way we could write that is 30 to 40 if you want to use interval notation. And so what does this mean in context of the problem? If D is increasing,
He's moving further away from home.
that's it. Easton is moving farther from home. Questions there? D, at which times is Easton exactly 1 mile from his home?
12 minutes and 65 minutes.
Okay, how did you get that? Very good. So on the y-axis, we're going to look for where we are at 1 mile. Which would be this line right here. Right, that represents being 1 mile away. And then I want to know, what times did this happen? Well, it looks like it happened right here. Which is about 12. And then like it happens again right there. And so the times that they come up with, the first one they wrote around 12. So because we can't see exactly where it's at, if we'll just use the word approximately or roughly, approximately at, they said 12 and 68. So I think you said 65?
Yeah, that's what I
Okay, so 65 is exactly on a crosshair because we're dividing into 5.
I think I looked at it wrong.
Yeah, so it'd be 65, it would need to be exactly here. It's a little bit right of there. So just give some rough guesstimation. Questions there? Any questions on 1 overall? Any parts of 1? 2, a function f is decreasing when x is between -5 and 0.
Students, last name beginning with the letters A through G.
I have no 10th grade students, do I? Okay. She's so loud, I need to turn her down. So if the function is decreasing from -5 to 0, increasing from 0 to 2, and constant when x is bigger than 2, there's lots of different ways you could do that. So if I'm just going to go from -5 to 0, decreasing, boom, I'm there. And then you start increasing from 0 to 2, boom, and then be constant. There's my graph. Okay, is that the only graph? No, that's not the only one. Let me show you the one they drew. Does that still fit all the same criteria? Where all mine were lines. Well, supposedly. Here they've got a parabola to start with. Is this decreasing? Yes, it decreases here. Then it increases as a line, and then it's constant here. The only one that has to be a horizontal line is the constant. There's no other way to draw a constant. But these could be parabolas. They could be curved. It just has to always be going up between 0 and 2. It has to always be going down from -5 to 0. All right, so again, these are just 2 possible solutions. There are several correct solutions. Here, a penny is dropped from the top of an Empire State Building from a height of 1,250 feet. The height of the penny in feet, t seconds after it is dropped, is given by the function h of t equals 1250 minus 16t squared. So when the time is at 0 seconds, what's the height of the penny? 1250. What about when we're 2 seconds in? What's the height of the penny? It's what? 1168? 1186? Okay. What about at 4 seconds? 994. 6 seconds? And 8 seconds. Man, I did that fast. Does everybody know where we get those values from?
No. My calculator won't do it.
It won't do it?
No, it kept telling me 0.
Can I show you a short way to do it on your calculator?
Yes.
Is everybody watching? Hey, watch this. Hey, watch. Hey, watch. Hey. Oh, it's low.
I'm not sure where to look.
It's gonna be up there.
Okay.
It's low. Okay, so if I want to put in this function, I'm going to go y equals. Make sure that's cleared out. I'm going to go 1250 minus 16, and for t we have to use x. So right here's the x button. 16x, and then squared is right here. Everybody get that typed in? And now let's go to second, and we're going to click window, which is table set. So what is our table starting at? 0, right? We got 0, 2, 4, 6, 8. And what are we going up by each time? We're not counting by 1s, we're counting by 2s in our table. So that's what the delta table stands for. How much is your table changing by? All right, now I've got that. I click second graph. Ooh. That'd be the quickest way, I think. Did it work?
Yes.
Anybody have an issue with their calculator? Did you know that calculator could do that? Pretty cool. Okay. Question 2 says, find the exact time when find the exact time t when the penny reaches the ground. So how could we find that? You guys tell me. How could I know when the penny hits the ground, the exact time?
Maybe h of 2 0.
That's one way. I like it. So if my function is h of t equals 1250, remember the h represents the height. So when it hits the ground, the height would be 0. Sorry, you can't see. See, y'all got to yell at me. I forget. I got to go back. And I'm not on my computer anymore. I'm back on my iPad. Okay. So the height is 0 when the penny is on the ground. So we could say 0 equals 1250 minus 16t squared. And now how many variables do I have in this equation? 1, so I can just solve it. When I have one variable, get the variable by itself. So for me, I would move the negative 16t squared over to the other side to make it positive. T is being multiplied by 16, so I'm going to divide by 16. That's going to tell me that t squared is equal to 78.125. And the t is still not by itself because it's being squared, so I can take a square root. Now remember this, anytime I choose to take a square root, I have to account for 2 possibilities, plus or minus. When I choose to take a square root, I must always use plus or minus. So t could be plus or minus the square root of 78.125. And what did you guys get when you put that in? It's an ugly number, isn't it? Does everybody know where the square root button's at on your calculator? Second x squared. I got 8.838834765. And so that is approximately, we're going to go to 3 decimal places, 8.839 seconds. So it takes the penny around 8.839 seconds to hit the ground. Any questions there? Can I show you how you can do that on your calculator? If you don't want to do all the algebra? Can I show you? Okay, so now I'm going back. So if I click, sorry, I have to kick it over here. If I click graph, right, this is showing me it should be a parabola. I can't really see what's going on because I'm so zoomed in. Right, so we could go zoom, click 3 to zoom out, and then click enter. I could do that again. Zoom, 3, enter. Oh my gosh. Zoom, 3, enter. Well, now it's way too big to make any sense of it. So let me go back to what it was before. So we should know the general shape of this as a parabola because it's an x to the second situation. Here, I was just trying to show you all the shortcut. Let me show you how you could really find the window. Don't be lazy, Cody. Okay, so if I click window, I need my x's to stay the same. So this is the x min to the x max. So when I look at my x's look good because I can see both of the x-intercepts. Right, so x's are fine, but I need to change my y's. So what is the maximum y value that I need? Well, when does it reach its apex? What's the highest point of this parabola? 1250. That's the height at which I'm dropping the penny. So I'm going to go to 1300 as the y max. Does everybody understand that? Let's see, there's a good looking parabola. Show me what's happening. Sorry, I was trying to be lazy because when you teach Algebra 1 kids, they really don't understand what all the window stuff means. But y'all guys got that, right? I mean, you can understand.
Students, if
Miss
your last
LaRue.
name
Oh,
begins
Miss
with the letters
LaRue.
H through Q and you are in the 10th grade, you can go to the high school library at this time to get your Chromebook if you turned in your Chromebook agreement. 10th graders, last name beginning with letters H through Q. Thank you.
So the question was, where does it hit the ground? Or what time, t, does it hit the ground? That would be right here, right? So I can find that value. Let me show you how you can find the value on the calculator. You can click second trace for calculate. And we are looking for, what's another word for the x-intercept? 0, right? You know all the names? X-intercept, 0, root, solution. Those are the main ones. There's probably one more that I'm leaving off. So we're looking for the x-intercept, the 0 of the graph. And now because there are multiple zeros, you have to choose which boundary we're looking at. So the left bound, the way that I used to do it is I used to scroll over. I'm just picking some point that is left of that x-intercept. So this could work here. You see how I scrolled? What I learned at my training is I think I can actually just put in the number. So if I want left of that x-intercept, I think I know 6 is left of the x-intercept. What's the number that's right of that x-intercept? Because now it's looking for the right bound. So again, you could scroll to click enter, or you could just put in a number. Looks like 10 is too far to the right. Do you follow me? When I'm putting in boundaries. So this left bound and right bound is giving me field goal posts, essentially. I want to know where's the x-intercept that's between these two lines. When x is 6 to x is 10. Then it tells me to put in a guess. I guess that's just in case you put 2 x-intercepts in there and you didn't know it. So my guess is it's about 9, right? So let's just say 9. Then it spits out at me what my x-intercept is. It's 8.8388. There's that number we found. Do an algebra. Right, so that's another way you could do it on that calculator. Am I giving you too much calculator information already? I need to slow down. Okay. We'll ease our way into it. Let me ask you this, just so we can practice with a calculator. See if you can find the other x-intercept on your calculator. The one that's negative 8.838. You cleared the graph? You cleared your y equals out? So you guys, do you have like no, did y'all use those calculators at all last year? At all in Algebra 1? So you've used them never. Okay. I made my Algebra 1 kids use them. So we're clicking second trace for calculate, and we're looking for the 0, right? So 2's the 0. So if I'm looking for this one, what is my left boundary? That means pick any x that's too far left of that x-intercept. So negative 10 is too far left, right? You could pick negative 30. You could pick negative 100. Doesn't matter. You're just picking some x that you know is too far to the left. Now pick an x that you know is too far to the right. You got a question? Everybody good? Are you using this for negative? This button down here? You're not clicking minus, are you? Let me come look. Let me look. So we're clicking, yep. Click 2. Enter. No, sorry, not enter. So now it's looking for the left bound. So we're putting in negative 10. So negative 10, enter. Then pick a right boundary. So just pick something that's too far to the right. That's fine. And then give your guess. About where do you think it's at? It's around negative 9, right? I mean, it's close to there. It doesn't really matter what you put as your guess, just to be honest with you. And then now it's telling you the 0 is at. Okay. Yep. Anybody else? My right bound was, let's just put 0. It doesn't matter. Guess. I'm going to guess it's at 32. I mean, to show you the guess doesn't matter. Oh gosh, it didn't like that. Okay, never mind. So let me pick something that's inside my field goal post then, I guess. So if I go second, calculate the 0. So if I go between negative 10 and 0, and I guess it's at negative 1, that's not really close, but it still gives me the correct one. So I guess just pick something inside your goalpost. So here it says find the average rate of change in the penny's height during the total length of its drop. Well, what keyword am I seeing here? The average rate of change. The slope. I'm finding the slope of a line. If I connected 2 lines for the entire drop of the penny. So what are my 2 points then that I'm going to plug into the slope formula? If it has to be for the whole ride of the penny, right? Well, it starts at time being 0 and it's at 1250, and it ends at time being 8.839 when its height is 0. Those are the 2 end points, the beginning to the end. That's the entire length of its drop. And now I'm just going to plug into the slope formula. So this would be y2, 1250, minus y1, 0. x2, 0, minus x1, 8.839. So this is 1250 over negative 8.839. Somebody do that calculation for me, please. Negative 141.4. Hold on, it lagged on me. 0.419, and this would be in feet per second. which means on average, the penny is falling 141 feet for every second. Now 4 says, determine how many feet the penny fell during each 2-second interval. So we're looking over equal intervals. Remember, I made you put a star over that equal intervals in the X, or over the domain. If it's linear, we should have equal intervals over the range as well. Well, we kind of know it's not linear because we've already graphed it, right? But let's look at the intervals here for a second. So I'm going to fill these values back in. So here, do I have equal intervals in the domain? From 0 to 2 is plus 2. From 2 to 4 is plus 2. From 4 to 6 is 2. 6 to 8. So I have equal intervals over my domain. Check. Now let's check and see what the intervals are over the range. To go from 1250 to 1186. So I would do 1186 minus 1250. I went down by 64. Okay, what about from 1186 to 994? So 994 minus 1186. It's what? Negative 192. 674 minus 994. Negative 320. And then from 226 minus 674. 448. So what do we notice? Is the change in height constant? It's not. The change in height continues to grow. Right? It's not constant. So the number of feet fallen keeps increasing. So let's say it's not constant. The change in height is increasing. So let's just think about what does that really mean is happening. If my change in height for each interval is increasing, that's it. That's what I wanted you to think. The penny's speeding up. It says complete the table with the average rate of change of the height of the penny. So what would be the average rate of change between 0 and 2? So let's think about it. What was my change in y between 0 and 2? It was negative 64. Everybody follow me? What was my change in x between 0 and 2? Nope. Listen again. The change in y's was negative 64 from 1250 to 1186. What was my change in x's? 2. So what would be my rate of change? Negative 64 over 2, which is negative 32.
Last names R through C, 10th grade. Thank you.
So now let's do the same from 2 to 4. So the change in y from 2 to 4 was negative 192. The change in x is 2. So if I divide those, I get negative 96. Everybody follow? Okay, what's the next one? It would be 320 divided by 2, which is 160. And then 448 divided by 2 is negative 224. So I've got a table of all of the rates of change for each interval. So we said, is the penny speeding up, slowing down, or falling at a constant speed? It is speeding up. How do we know that? The average rate of change is getting more negative, right? So the average rate of change is getting more negative. Which means a faster rate. Okay, 7 tells me to graph my function. So I'm going to look back at those points I had at the very beginning. So those would be the points 0, 12, 50. Then I had the point 2, 11, 86. And then I've got 4, 994. Six, 674. And 8. What am I doing? Just leave me alone. Leave me alone, okay? 4, 994. And 6, 674. 8, 226. And then I know at like 8.8, I'm at 0. And if I just connect the dots between them, it should be part of a parabola, right? That's what I'm looking at. It's not a line. So the next question, is this concave up or concave down? Okay. It is concave down, but do you know what the difference is between concave up and concave down? Not always, right? That's the interesting part. The way that I think about it is, I either have an umbrella or I have a cup that will hold water. So if it's an umbrella, it's concave down. If it's a cup, it's concave up. And I know you think that's exactly what I said. Okay? But we're eventually going to be getting at lines that have multiple curves in them. Okay, we're going to be graphing polynomials. So in a polynomial, from here to here, that's making an umbrella. This is concave down. But then at this point, right here, up till here, it's concave up there. So it can kind of get confusing between, even though the graph is, like here, the graph is still increasing, but it's starting to make an umbrella. It's starting to turn down. So it is concave down from here to here. And then concave up from here. It might change concavity right there. I can't tell. It looks like because of an arrow, it probably shouldn't. Right? It should probably keep going up. But think about it as cups and umbrellas. This one's concave down, which means what in terms of the problem? The rate of change is decreasing, which means the slopes are getting more negative. Do you remember when we were talking about tangent lines? Lines that only touch the graph in one spot instead of two? So look what would happen if I drew a bunch of tangent lines here. So if I drew a tangent line here, think about the slope of that tangent line. Say it touched the graph right here. I know it didn't, but it's supposed to. But what if I drew a tangent line here at It's so hard on here. All right, so say that should have bounced back off, right? That's going to be more negative. You see how the slope of my tangent line is more negative? And the farther I go down, it continues to get more negative, my tangent lines. We'll finish up Monday. Try